Okay, and the last speaker of the afternoon session is Steve Vickers from the University of Birmingham that will talk about arithmetic universes, home of free algebras.
Thank you, Christian. And thank you for inviting me to this talk. The last time I saw Eric was just after the formal topology workshop in April last year. He came and we had a one-day workshop that was birthday celebration jointly for myself and Giovanni Sambin. And Eric kindly came and gave a talk on the relationship between Milo-Calic completion and Bishop's constructive mathematics that Eric had worked out. So it was a shock in November to discover that he had died. But now, under sadder circumstances, I'm returning the compliment, so giving a talk about his work. The only paper we actually written was partial Horn logic and Cartesian categories. And looking back at it, I'm not actually sure how it came about at all. It was somehow a combination of Eric's logical interests and my own interests in the initial model theorem, which I'm going to explain a bit more in terms of arithmetic universes, but also it tidied up a question that had been in my mind ever since my PhD thesis in the late 70s, when I was trying to work out how to use generators and relations to present abelian enriched categories. And I had a very complicated way of doing that. And later I discovered that this was a special case of a known theorem, but the work with Eric gave a nice clean way of describing the construction. So that's what I'm going to summarize in the talk today. So the background is the initial model theorem, and this is in Barr and Wells, the TTT book, and it says every Cartesian theory has an initial model. Cartesian is the same as essentially algebraic, if you know what that is, or finite limit theory. And once you've got initial models, then there's a whole lot of universal algebra you can do. You get free algebras, you get presentations by generators and relations. And that was my particular interest. So what we did in the paper together was we simplified the account of that using a logic of partial terms instead of total terms. And the theories themselves were simplified by Horn clause axioms in a partial logic, just using equality and conjunction. And the proof of the initial model theorem used a simple construction from the algebraic case, which I'll call the term congruence construction. And that is just make an algebra of terms and then generate a congruence, factor out the congruence. And as an example we mentioned in the paper, and which I'm going to elaborate on today, we talked about classifying categories or syntactic categories as initial models. So the outline of today's talk is part one. I'm going to say more about arithmetic universes, which we barely mentioned in the paper, but they somehow occupy the sweet spot of the initial model theorem. And internally in arithmetic universes, you do have free algebras. Then part two is going to say a bit more about classifying categories and the algebraic approach that's suggested by the paper. And then part three is a grand generalization, much of it's some with some solid work, but some also speculative, which is on generalized topological spaces. And that's using classifying toposes. And by using the AUs, we can substitute for the classifying toposes, and potentially we get a foundation for all of continuous mathematics. And I'm going to finish up at the end of that by saying something of what that would mean to have a foundation for continuous mathematics instead of foundations for ordinary set-based mathematics. So let me start off, I've said that. Let me start off with a little history of arithmetic universes. So they actually come from some work of Joyal, and he used the initial arithmetic universe to give an account of Gödel's incompleteness theorem. Now that never actually got published, although there are unpublished notes circulating, or outlines of the proof. And because so much is unpublished, I hope if I make any misrepresentations of the history of these things, people will accept my apologies for that. Then Gavin Wraith, who was obviously in on the work, he reported it at a conference that I attended. This is the 1985 Categories in Computer Science conference at Guildford, but he didn't write it up. So it's more of the unpublished folklore. And both of them, I know, were aware of the potential for AUs to have internal free algebras, which is what I'm going to stress. And, you know, I'd been in discussions with them, and in my topical categories of domains, 1999, which was using classifying toposes, I suggested using arithmetic universes to give a base independent geometric reasoning. So not relying on classical sets, but on potentially constructive base toposes. I think even so, there was not much going on in arithmetic universes until Millie Maietti set out some rather path-breaking papers. So she was the first to set out the current definition, and she proved its major properties. And then following on from her, Millie and I did a joint paper. I've done two more recent papers on sketches for arithmetic universes and how to use them for classifying toposes. And with my student Sina Hazratpour, we've elucidated we've exploited the AUs to give proofs of vibrations and opt vibrations in the category of toposes. I should also mention Paul Taylor, who was also interested in these things, and he wrote a paper showing that the category of overt discrete spaces in his abstract stone duality is an AU. So somewhat like the category of sets. Okay, so here's the kind of core of what's going on, and this is the initial model theorem. And I'm going to start with a simple case that is very well known and really pretty easy to see. And that's for algebraic theories. That's a theory described just using some finite tree operators and some equational axioms. And the theorem says every algebraic theory has an initial model. And the proof is really quite easy. This is what I'm going to call the term congruence construction. So you start off, you form a term algebra to interpret the signature, that's the operators, all possible terms. Then within that, you generate a congruence inductively from the equational axioms that you've got. Once you've got the congruence, you factor that out, and that models the axioms, and then you have your model of the algebraic theory, and it's the initial model. So that's quite easy. And once you've got initial models, then you've got, first of all, you've got generators and relations to present algebras. So if you want a model, if you've got a theory, algebraic theory T, and you want to make the T algebra presented by generators G and relations R, then what you do is you take the theory for T with its operators and you add some new constants for all the generators. And then you also add axioms for the relations in R. That's a new algebraic theory. And a model of this is a T model equipped with function from G that respects the relations. And TGR, the the algebra presented is just the initial such algebra. So we know its existence from the initial model theorem. And then free models are, if you have no relations at all, you just say some generators, then you get the free models. So although the title of my talk was Home of Free Algebras, I mean, really, I mean home of initial models, home of presentation by generators and relations, all that kind of stuff. Okay, so that's the algebraic case, which is fairly simple. But it's also true, and this is a bit harder, this is a bit more complicated, for essentially algebraic or Cartesian theories. And I'm not going to, I hope you get the exact definitions of these. You can see an overview of the equivalents in my paper with Eric. But perhaps the simplest way to understand them is with essentially algebraic theories. So there, you've still got operators, but they may be partial operators. And for each one, the domain of definition is defined using equations involving previous operators. So it's some kind of well-founded order on the operators. And then axioms say one term equals another, S equals T, whenever both sides are defined. Okay. Now, an alternative description, which you see in the Elephant, volume 2, D 1.3.4, is of Cartesian theories. And so there, the logic that you're using is a regular logic. It's got equality, conjunction, and existential quantification, except that the existential quantification must be provably for unique existence, not just arbitrary existence. And then the axioms are sequence. So you've got two formulae phi and psi built up with these three connectives. And you're in some context X, list of free variables, and the axiom says one formula entails another. So these are equivalent, and again, and they're equivalent to finite limit sketches. And as I mentioned in Barr and Wells, you see the theorem that every Cartesian theory has an initial model. Now, the proof of that is a little complicated in Barr and Wells, but let's have a look at some of the examples. Really important example is categories, and you've got two sorts, object arrows, and composition is the partial operator. It's a binary operator on arrows, but it's only defined if the domain of one equals the codomain of the other. And you can use similar techniques for other kinds of categorical structure. So for instance, pullbacks, again, you've got some partial operators, binary operators on arrows defined if they have the same codomain, and they make a cospan. Same argument applies to push-outs. Another example is enrichment as operators on Hom sets. You get operators on parallel arrows. One example, important example, is elementary toposes with natural number objects. And this idea really underlies a lot of the methods of Lambeck and Scott and how you construct a free topos, free elementary topos with NNO. And the final example I'm going to say more about is the arithmetic universes. So those are some examples of Cartesian theories. Here are the arithmetic universes. And Milley described them as pre-toposes with parameterized list objects. I'm not going to say that much about sorry, I'm just wondering if I can write on this. Here we go. So I'm not going to say too much about this, but this big square here is the universal diagram that's needed for list objects. Basically, list A is the object of finite lists of elements from A. And the way the universal property works is that if you have any object Y with a with a map G that really says how elements of A can act on elements of Y, so it's a map from A cross Y to Y, then what you're trying to do is extend that action from single elements of A to lists of elements of A. So that's going to end up with this vertical morphism down there. The parameterization is just a little bit of extra that that says how you can use some object B to parameterize the starting point, the kind of initial point in Y where you start applying things. So unless anyone particularly wants me to dwell on that, I'll skip on to the next slide. Oh. Not so easy. Right. So pretoposes, I suspect a lot of you know about pretoposes anyway. So you've got finite limits, finite coproducts, coequalizers of equivalence relations, and axioms to make them cooperate well with each other. Now, not true for an arbitrary pretopos, but is true when you've got list objects. They also have all finite coequalizers. And essentially, this comes down to the ability to use the list objects to define transitive closures of binary relations. So, so these have all finite colimits. And it's not hard to show from this. So it's in my joint paper with Millie, and it's also in my sketches for AUs. The theory of AUs is Cartesian. So once you've got the initial model theorem, then you can present AUs by generators and relations. So that's a key property. Okay, so the initial model theorem, once you go to Cartesian theories instead of algebraic ones, the term congruence construction has problems, and the Barron-Wells proof is really very different from this. So the problem is, the first step was to make the term algebras. So if you try and do that, you really only want the defined terms. You don't want undefined terms. But remember, domains of definition are defined by equations. So when you generate a congruence inductively from the axioms and factor out the congruence, you've created more equations. So you get more defined terms. So more than just if you took the known defined terms from step one. So on the face of it, you have to iterate this. So there's a question, how many times do you have to iterate it? And that obviously is going to be slightly sticky. So what Eric and I did was to use a logic of partial terms. And so this is actually a very straightforward adaptation of first order logic, first order logic as presented in the elephant. We just needed some extra rules for substitution, because you can only substitute defined terms for free variables. And in terms of that logic, the term congruence proof has an alternative possibility of how to proceed. So for the term algebra, well, don't worry about whether they're defined or not yet. Just define all partial terms. So it may or may not be defined. Now, the next step, generating the congruence, we actually generate a partial congruence. It's not necessarily reflexive. Remember, the reflexive rule that says A equals A, T equals T, isn't going to hold in general unless we can prove it from the axioms, because that says where the partial operators are defined. So So what we're going to get from our inductive generation from the axioms is just a partial congruence, but then we can factor it out. What that means, it's like we factor out a congruence on the self-equal terms, the defined terms. So once you've done that, you've already got your model of the Cartesian theory, and this is the initial model. So you don't have to iterate, you just do a single step, but using partiality on the way there. So that was part of the paper. The other paper was to get an alternative representation of Cartesian theories. So we used, in this partial logic, a quasi-equational theory, and that we define that as a Horn theory. So we've still got a signature of sorts and operators, no relation symbols. So it's really going to be just like an algebraic theory. The logical connectives are just equality and conjunction. The axioms are sequencing context. So conjunction of equations on the right, well, that's what you'd expect from the algebra anyway. The only slight difference is we can also have conjunction of equations on the left. And what we showed is that those are equivalent to Cartesian theories. So now our term congruence proof of intermediate value theorem is, first of all, you express the Cartesian theory in quasi-equational form, and then you use the term congruence construction for partial terms, and there you go. So that seemed a lot simpler than what you see in Barr and Wells. Now, arithmetic universes, let's go back to them. We know now they're a Cartesian theorem. We can present them by generators and relations, but also internally in arithmetic universes, the structure supports quite a lot of stuff. As you might guess from the fact we got list objects, it supports list processing, including concatenation, and in fact that makes list A a free monoid on A. You've got arithmetic on the natural numbers. The natural numbers are there because that's list on the object 1. Millie proved that you've got free categories on graphs, free category action from graph actions. So that was, that was already in the air from what Schweil and Wraith were thinking. Then Millie proved that initial models exist. She used type theory, but you can also replicate the term congruence construction. You use reverse Polish notation to represent partial terms, and there's a bit of syntax checking, making sure they're well formed. That comes out of the AU structure. And then you do the same thing really for proof terms as well to generate the congruence. So I say that with my fingers crossed because that's, I haven't, and as far as I know, nobody else has written down exactly how to do that, but it seems fairly clear that that's what you expect to work. So, so the arithmetic universes, they occupy a kind of sweet spot for the intermediate values theorem. The theorem itself is valid within AUs, but it can also be used to present them. So you'd get the same with elementary toposes with NNO, of course, but the AUs are more general than that. And what this leads to, that sweet spot, the two-faced nature of them, is that you get stuff can be internalized. So one special case that's already important was the original AU has an internal initial AU, and that's what Schweil used and proved by explicit concrete construction. And the existence of natural numbers gives arithmetic, which you need for Gödel's theorem. And then the Gödel gap between truth and proof is the gap between external and internal. And more generally, that you can you've got nested internalization, which means the constructions can be carried out at different levels of internalizations. And what the mathematical consequences are of that, they're surely profound, but we still don't understand very clearly what they're going to be. Okay, so part two, that was the AUs. Part two is now this algebraic approach to classifying categories or syntactic categories. So what this says is really logic, and I'll call L for a particular logic, you know, logic saying which connectives you're using and so on, is really about a theory of categories with structure. The structure, you need to interpret the logic, and you expect this to be a Cartesian theory. Normally it is. And then within a logic L, an L theory really is a presentation by generators and relations of categories with that structure. So the generator, roughly, the generators correspond to signature sorts and symbols, and relations correspond to axioms in the theory. So if you think of a theory as signature plus axioms, they're pairing up roughly with generators and relations. I say roughly because it gets a little bit more subtle than that. The relations, suppose you've got some relations can say some sorts in the logic, you know, should be part of the signature, are derived from other ingredients. For instance, with logic of AUs, sorts can be derived as limits and co-limits and list objects and more general constructions of that. But what I'm going to say is, well, let's just take the algebraic point of view that the logic is the Cartesian theory of categories with structure, and the theories are the presentations. And then the classifying category for a theory is the category presented by the theory as generators and relations. The universal, I hope you're not seeing those things popping up. The universal characterization of classifying categories says that for any C with that structure, the T models in C correspond to the L functors from the structure preserving functors from the classifying category to C. Okay, so the classifying categories are useful because they can be thought of as the class of T models without regard to the category C where the models are taken. So what happens then is if you have a structure preserving functor between the classifying categories, you can also think of this. See, this functor is going from right to left, but you can also think of it from left to right as being a model transformer. So a model of T0 is like M functored to some C by the universal property. Composing that with F gives you a model of T1 in the same C. And so this is going to be F of M. And it's there, you get it basically by substitution. And it's also important to look at how these functors might exist. The universal property says that F here, right, is going to correspond to a model of T1 in the classifying category, the T0. Now, everything that's in the classifying category for T0 is generated by T0 as generators and relations. So if you think of a kind of, if you think of a declaration, let M0 be a model of T0, right? So this is like declaring a formal parameter of some construction. And then you draw a box around the scope of this declaration. And within that box, you're just using L constructions categorically. Then really what you're doing there is constructing stuff that's inside the classifying category L of T0. This box is L of T0. And if with your construction at the end, you get a T1 model, then that's exactly what you needed to do to get your functor F that is up there. So these functors F are just like kind of subroutines that take M0 as a formal parameter and then do some stuff and then return a result at the end. And when you apply it to an actual parameter, which is this specific model M, then that's just going to be substitution. Right. So this is sort of getting beyond the algebra and thinking, putting yourself into the frame of mind where this stuff really is about classes of models.
Can I interject there, Steve, on that slide? Drawing a box like that, is that sufficient, or what more do you need to do to ensure that F is an AU structure preserving functor?
It's the fact that these are L constructions. They're, it's not just AUs, it could be other logics as well. But all these constructions are using the operators for categories with the L structure. So that means that everything you do here can be interpreted inside the classifying category. Is that answer? Yeah. So it's that L that's important. Does that answer your question, Paul? Yeah. Okay, so some questions here. One is, can this be made for type theory? I'm not actually sure. You'd think there would be a similar way of getting classifying categories for type theory, but I don't know how you do it. I suspect other people have worked on this and got results that I'm not aware of. Yeah. Another thing is, for AUs, does it classify models in an ambient AU? So the way we've got it, each C where the models are sought is small. It's internal in the ambient logic. So if we've got a model with the sorts indexed by T in the ambient logic, but we're assuming it's still AU logic, can that be extended to indexation by the classifying category? So I don't know. It ought to be true, but I don't know. Strictness, right. We actually had problems with this, which we think we solved in Millie and I in our paper. But here's what the problem is. When I said the L functors from classifying category to some C correspond to the T models in C, well, first question there is, are they strict L functors? Do they preserve the structure on the nose? Are they strict T models, again, preserving the structure on the nose, or are they non-strict? And then corresponds, we've got two categories that we're comparing here, category of T models, category of L functors. Do they correspond up to isomorphism or up to equivalence? The usual interpretation is that they're up to equivalence. Now, the algebraic use of the initial model theorem tells you quite plainly that they correspond up to isomorphism. So what's going on here is that for the algebra, which I would say is really for the syntax, we require up to isomorphism, and we require everything to be strict. So strict functors here, strict T models here. Semantics, that is just, you can't live with that. So you have to be able to deal with non-strict models. So it has to be up to equivalence. So how do you connect the two of those? Well, in my sketches for arithmetic universes, I solved this problem with well, with various steps. So the first one was that I was using I was using a sketch formulation of the theories, because then it's fairly easy to talk about both strict and non-strict models in the same context. Normally with sketches you talk about non-strict models, but it's perfectly easy to adjust the definition and have strict models. Then within that, I restricted the way sketches were going to be built up. So the sketches I used, I called, well, this was with AUs, but I think it would work with other logics as well. I called them contexts in order to get a theorem that every non-strict model has a canonical strict isomorph. Now, what could go wrong? Well, what could go wrong is if your sketch says that some limit is, for instance, equal to, on the nose, to some co-limit, then it's actually quite hard to get strict models of that. A non-strict model would simply say they're isomorphic, which is a very mundane thing to want to do. So the restriction to the sketches, what the contexts do is they say, well, when you say that something is when your sketch specifies that a sort is a limit, that sort has to be fresh. Can't be a sort that already existed. So, if you've got one limit and one co-limit, you've got two sorts that have to be different from each other. Now, to say they're isomorphic to each other, that's easy with the sketches, but you can't say they're equal. So I think this is a kind of, it's ruling out evil, I suppose. It's about not having arbitrary object equalities. And then once you've got that, you've got the canonical strict isomorphs, and you find that the classifying category also classifies the non-strict models, and then it's up to equivalence. So the AAU contexts, I investigated the two category of contexts, which I called con. I'll come back to that later. Now, part 3. So here's we get on to not generalized classes or models, but generalized topological spaces. So classifying toposes are really the same idea as the classifying categories, but they're complicated by having to have infinite disjunctions. Okay, so for a generalized classifying toposes, generalized space of T models, you need arbitrary disjunctions in your logic, or at least some infinite disjunctions to match unions of opens. So that takes you on to geometric logic, and actually you really need arbitrary co-products as well. Okay, now the idea of classifying topos is really that, classifying categories, really then you want to talk about theories. So this now is getting onto point-free topology. So the theory T is a geometric theory of what the points are. Okay, and let's have a little digression onto the right about different phrases here. So I've said, first of all, I want to distinguish between point set and point free. So point set means the points are elements of a set. And point free, in line with the classifying idea, is the points are models of some theory, which now is a geometric theory. Right, so that's point set and point free. Let me talk about two other words as well. So pointwise is the way you describe reasoning when you're happy to talk about points. And I'll call pointless reasoning that avoids using points, just talks about the algebra. So if we look a few slides back to these boxes, actually this is pointwise reasoning. So we've said let M M0 be a model of T0, that's a point of the codomain space, sorry, the domain space. And then we construct a point of the codomain space. So point-wise reasoning is perfectly okay for this use of classifying gadgets. Whereas if you somehow wanted to do without the box and just define the F explicitly in some way, that would be more pointless, right? And, you know, pointless sounds disparaging. I think I do mean it to be disparaging. I think you don't need to be pointless. You can reason point-wise in this style. Okay, so what have we got? The logic L needs to be geometric, or I'm going to say in a minute, arithmetic. T is a geometric theory of points. L wanted arbitrary disjunctions. Well, what does arbitrary mean? Let's introduce, let's take your favorite category of sets and call it S. And suppose it's an elementary topos with natural numbers object. So arbitrary is going to be S indexed. And then once you've fixed S, then you can make the classifying topos, which let's write it S square brackets T, which is reasonable enough. By the way, geometric, I'm talking, these are going to be generalized spaces in Grothendieck's sense. So the geometric theory T is first order geometric theory T. And the ungeneralized case or localic case is with propositional geometric theory. So that's what generalized means there. So, so there's going to be here geometric reasoning as a point-wise treatment of point-free spaces. Now, the theory of bounded S toposes is not Cartesian. So, so ST, the classifying topos, has to be defined in a more concrete manner, which is why you get the pre-sheaves and the sheaves. And it's characterized only up to equivalence. You don't have immediate access to the Cartesian theory ideas. But AU contexts are sufficient in practice. So the real line can be, Dedekind sections, points of the real line, can be described as models of a AU theory. So Millie and I discussed that in our paper. And really what's going on there is you've got the internal categorical constructions of the natural numbers. You can use that object to express countable joins in the logic without actually having countable disjunctions. So let's try and reverse engineer this notation that ended up with S square brackets T being the classifying topos. Let's try and strip off the S and just write square brackets T for something that is going to be the space of T models without worrying about what S is, because for AU contexts, S could be any elementary topos with NNO. So this square brackets T is the notation for the formal dual of the classifying arithmetic universe. And so we're going to think of this as the space of T models. That's the mathematical manifestation of the space of T models. If we didn't do this way, we'd have to choose RS. But T gives a site in any S that we might choose. And then once we've done that, we can make the category of sheaves with respect to S, sheaves over that site. And so I was using this technique in my paper, Arithmetic Universes and Classifying Toposes. So now...
Dual mean? What does the word dual mean in this context?
Sorry, say it again.
The word dual.
Oh, okay. Formal dual means it's the same thing, but in a formally dual category where the arrows have been reversed. Like locales being formal dual of frames.
Okay, okay, right, okay. I thought there was some lineological something like that.
No. So we actually get if you fix any S, we get a two functor from the two category of AU contexts, which I mentioned earlier, to B top over S. That's bounded topos with bounded geometric morphism sliced by S. So that look in the elephant, that's the big hero of geometric logic. That's where the Grothendieck topos is with respect to S. That's where they live. So S is now irrelevant. We've got a base independent treatment of classifying toposes. Okay, this is my paper, Arithmetic Universes and Classifying Toposes. The other one, Vic 99, yeah, that's notation. I introduced this notation in topical categories of domains in a previous century. So anyway, so the choice of S is irrelevant, but you can do it over any particular S, and it works vibrationally over choice of base. Works happily with change of base.
Steve,
yeah,
is that functor an essential surjection, as in every bounded topos over S comes from a con, or
no? Absolutely not. Absolutely. Okay. No, this is an approximation, but the thesis is, or the dream is, that this is enough to give you the maths that you actually want. And in B top over S, you've got loads of stuff that's irrelevant, really.
Oh, okay. So you're sort of carving out the bits of it that you think is relevant.
Yeah.
Okay. Thanks.
Okay, so there's some dependent type theory in here, or waiting to get out of here. So this comes from ideas of bundles. So when I say bundle, I mean describing a map by the assignment of, for each base point, you say what the fiber is, the fiber as a space. So if you've got a context extension, you've got a smaller context and a bigger one, and that gives you a map between the spaces, which is just by model reduction. Given a model of the bigger theory, you forget all the extra stuff, and you get a model of the smaller theory, right? So this can be treated as a bundle. If you've got a base point X, that's going to be a model of T0 somewhere, and let's say it's in a elementary topos with N and O. You've got a base point X. We want to describe the fiber as a space, so we can actually describe it as a bounded S topos, which is going to be a Grothendieck topos relative to S. So what we do is we given S, X, which is a model down here in S, we actually get an S geometric theory. And perhaps in answer to Christopher's question, this is not going to come from a context. So you've got an S geometric theory of T1 models Y that live over X, P of Y equals X. So you can then classify this theory and get S T1 over X with a bounded geometric morphism down from one to the other. And it's the way this is made, really, this T1 over X is you've just substituted the specific model X for the logical ingredients of T0, done that substitution in T1, but it's only going to work in S. It's not something you can just do in AU contexts. X really does live in S, not somewhere else. And this construction is preserved by pullback along geometric morphisms. You've got a geometric morphism F, goes from S prime to S, doesn't even need to be bounded. Then you can substitute F upper star of X for X. You get another geometric theory over S primed. You can get the topos of sheaves, and it turns out this is a bi-pullback. So really this idea that the substitutions correspond to the bi-pullback, that seems to me to be saying that there's really dependent type theory stuff living there and just waiting to be expressed out. We've got a semantics waiting for a type theoretic syntax, but don't really know how to do it yet. Okay, so some general examples, sites. Suppose you have, if you've got a localic S topos, we can express that as a fiber over some point. So how do we do this? The T0, the downstairs theory, is a theory of frame presentations. So I've written about those as GRD systems. That was in my paper on double power locale and exponentiation. T1, the extended theory, is GRD system equipped with a point. So any frame presentation, E and S, downstairs, that's down here, gives you a topos of sheaves upstairs using this construction, and that's and a localic geometric morphism. And that's just the well-known Joile and Tierney equivalence between internal frames and localic bundles, except that now we're not really dealing with frames, we're dealing with frame presentations, and that allows it to be done geometrically. And I used that idea to show that power locale constructions on bundles work fiber-wise. So again, this is some dependent type theory. So the power locale can be represented as an endomap on T0. That is to say, a geometric construction or an AU construction, in fact, that takes a presentation and gives you another presentation. You can do something similar with arbitrary bounded S toposes. You have T0 downstairs is the theory of sites, T1 upstairs, theory of sites equipped with continuous flat pre-sheaves. And that's again how you make a bounded geometric morphism. So AU logic has a potential to address topos theory. Now the questions here, how do you address continuous maps, which is bugging me, because not every space is exponentiable, so you can't classify them. Why are power locales functorial? Well, actually, I've got a proof, although I'd like to make it more general than just the power locales. Sorry, on my screen. Can you read the bottom line on your screen? Anyone?
Yes, you can.
Yeah, I can't.
It says exploit internalization, use theory of AUs equipped with sites. Does that help?
That helps. In fact, I don't even need to say it myself now.
All right, awesome.
Okay. So how are we going to exploit this continuity of AU reasoning? And this is important because some non-AU constructions are intrinsically discontinuous. So here's one, the exponential function types. So the natural topology on the exponential y to the x, it does exist as a space, but it's not discrete, it's compact open. So if y to the x is still locally compact, we can exponentiate it again. Then we'll get some z to the y to the x. There will be an answer that comes out, but the topological answer will be different from the set theoretic answer. So what have we got here? Z is discrete. Y to the x, unfortunately, isn't. It's compact open topology. So it's harder to be continuous. So we're going to get fewer points in the topological one than in the set theoretic one. We're going to get different answers. Similar thing with subobject classifier and power set of x. The topology is Scott. So again, if you try and if you take z to the power of some power set, you will get fewer points than you thought, just because it's harder to be a continuous map from px with a Scott topology than it is from px with discrete topology. So in AUs, the discrete topology isn't even something you can express. So you have to go with the topological route, and you get some different answers. Here's another one, final one. If you have a universe U, that is really, from the topological point of view, a discrete approximation, one of many, to the generalized space classifier, space of sets, the object classifier for the theory with single sort and nothing else. So what's going on here, if you've ever seen Richard Garner's interesting paper on ionads, which I might characterize as point set toposes, you see something rather similar. You get sort of, the universe is just one of many. And again, when he's discussing his ionads, you get sort of families of sets that are trying to be the set of points for which, unfortunately, we know it's a proper class, but I'm saying actually it's a generalized space. So again, if you exponentiate, you get different points. A map from set to set, the continuity conditions say it has to be functorial. If you just define it geometrically, a consequence is it has to be functorial. That's just automatic. And also it has to preserve filtered colimits. So you find that set to the power sets is the space of diagrams over a category of finite sets. U to the power U is going to be something different. I don't know what it's going to be. So you'll get different answers. So we've really got two different foundational approaches from sets to spaces. So the big one that we've got and everyone is used to starts from sets, including the arrow types. And that, right from the start, that allows discontinuities. So if you want continuity, you need to have a bureaucracy to disallow the discontinuities. So there are various ways we know of doing that. You can use point set spaces, you can use frames, sites, geometric reasoning, all sorts of things. But you need bureaucracy to disallow some of the stuff that you thought was just part of your logic of sets. The discontinuity can still appear when you're constructing sites. So, for instance, I mean, this is just an example plucked out of many, but the space of non-trivial rings, right? Apparently that's a presheaf type, but that relies on having a category of non-trivial finitely presented rings, and saying when a finitely presented ring is non-trivial relies on deciding the word problem for that, which I believe is not computable. So, with the AU logic, you wouldn't be able to get that category of non-trivial finitely presented rings. So, what's going on here is it's not really a presheaf topos. it's a closed subspace of appreciative topos. Unfortunately, often we don't know how else to do the topos theory. So, you know, all over topos theory, you get discontinuous constructions of size. Now, AU logic, on the other hand, we don't need any bureaucracy for point-free spaces. We never had the discontinuity, so we don't have to disallow it. And point-wise, this is the point-wise reasoning. A map is point maps to point, bundle is base point maps to space, or theory for the space. And somewhere in there should be a dependent type theory of spaces. And the idea is introduce discontinuity later, if you have to, right? And maybe you don't. So the pros of this AU mathematics, you know, if we can get it going, is we've got point-wise reasoning for point-free spaces. So actually, we already have lots of geometric techniques that we know work. We've got fiber-wise topology of bundles. I think this is a fascinating idea. It's you know, a bundle as base point maps to fiber continuously. If you look at the point set topological idea of fiber-wise topology, this whole book of it by James, it's rather ad hoc, but this is a unifying principle that says how to make it work. So dependent type theory of spaces. On the other hand, use of arrow types must be justified. Y to the x is, as it happens, because x is locally compact, it's a space. And can we regain the deep applications of topos theory? Again, we don't know until we've put a lot more work into trying to find out. So now, just to finish off, here's a little present for you. So the mathematics is different, but excluded middle holes. So Millie and I proved this. This is right, constructively. So if P is a proposition, that's a subset of one, and actually that's the same as an open subspace of one. One is just singleton star. Not P, which is empty set to the power P. It exists, but it's not a proposition. It's a closed subspace of one. Its topology is not discrete, it's stone. It has comes from a Boolean algebra of clopens, and that Boolean algebra is generated by nothing. So all it's got is a constant 0 and 1, and they're equal if P is inhabited, if star is in P. So where P is inhabited, B is degenerate, so it's got no prime filters. On the other hand, if P is empty, then this equation doesn't come into force. B has still got two distinct elements, so you have got a prime filter. So that's how you get the right points in it. Not P, which is 0 to the power of 0 to the P, actually is homeomorphic to P. And you can use Stone's duality theorem to see this. So a Boolean algebra homomorphism from the clopens of empty, which is just the degenerate Boolean algebra, to the clopens of 0 to the P, which is what I wrote down there, right? So a map from degenerate Boolean algebra to here only exists if this equation comes into effect. So it only exists if star is in P. And following through the details, you find that 0 to not P is P. Join exists as join of subspaces. You know, we've got join of subsets, but we can't do that here because not P isn't a subspace. And calculation shows P join not P is equal to top. Meet exists too. P meet not P equals bottom. So we've got classical logic, and from this point of view of those subspaces, and from this point of view, the only reason classical logic went away was because we tried to treat this space, not P. In reality, it's a closed subspace, but we tried to take its set of points and treat it as a closed subset, and that's what went wrong. So conclusions, I'm going along. I think I said it all, so I'll stop there. I've already overrun.
Okay, thank you very much, Steve, for the talk. Let's give him a round of applause. And we have Paul that wanted to ask something.
Yes, I would to add a few things. So thank you very much, Steve, for your overview of arithmetic universe mathematics. Just wanted to add a couple little things. So recall that in topos theory, there's this sort of dichotomy between topos as a space and a topos as being a substitute for the category of sets. So you've been talking about the first point of view there. The other point of view is you've said less about an arithmetic universe as being a recursive version of sets. You also slightly hinted at the possibility that there might be some topology in this, and that's really the role that I envisaged in the relationship between arithmetic universes and abstraction and duality. That would be that the model of ASD would be the topology, the theory of topology that goes along with the arithmetic universe as being the theory of sets.
Yeah, although of course I was treating topology in the generalized sense.
I thought that in your last slide you were talking about almost a kind of topology that, as it were, goes on inside the arithmetic universe.
It's more subtle than that. It's how to put it? Okay, yes, you're right. Yeah.
Okay. But also, where you said continuous and topology, if the arithmetic universe in question is the free one, then it's all recursive. So
yeah,
all our continuous things are actually in principle programmed. That's another thing that I would like to see come out of all this this way of doing things.
Yeah, that would be interesting. So I've got this two-category con of AU context, and in there is an object that stands for the real line. So morphisms in there from R to R would, in some sense, be computable maps from R to R.
Yes.
Okay. Any other comment or question? So I just had a quick remark about this, the use of the arithmetic universes in the proof of Joyal of Gödel incompleteness. So it's finally been made available, Joyal's proof. So you can find it on, there's a preprint on archive. I'm not sure if you're aware of it already.
No, I'm not.
Is it the one by Alexander Fieterling?
Yes, exactly, that one.
Alexander's, yeah.
Gödel incompleteness after Joyal.
It's a pity that Alexander is not here in this meeting.
Indeed, yes. But at least the proof is there, and one can work out the details quite easily. There's the link that Peter sent, and they also have an application to Loeb's theorem as well with that.
Okay, good. I'm glad he's got that out.
Any other comment or question? Okay, then I suppose we thank Steve again. We have now finished the afternoon session.